Hello everyone, welcome to the 14th reading session. Today we have a paper with us, Thinking Fast and Slow, Efficient Text-to-Visual Retrieval with Transformers. There are 5 authors for this paper, Antoine Miech, Jean-Baptiste Alayrac, Ivan Laptev, Josef Sivic, and Andrew Zisserman. This is a paper that was published in CVPR 2021. We have 2 presenters with us, myself Sohan Patnaik. I am a third year undergraduate from the Department of Mechanical Engineering. I am a head at KDAG. Along with me, there will be Sibasmarak Panigrahi. He is a final year undergrad from Computer Science Department. He is an advisor at KDAG. So without further ado, let's begin. So let's see the outline of this presentation. First, we'll introduce you to the concepts proposed by the authors and what are their contributions. Then there are basically 2 approaches that are used for this whole retrieval task, that is the fast and slow steps. We'll deep dive into the slow model that uses cross-attention. Like the authors proposed a novel architecture for fine-grained vision text cross-attention. Also, they used a bidirectional captioning objective for retrieving. Next, we'll see how the faster module works. How is it indexable? Like how exactly is it working and how is knowledge being distilled from the slow model? And finally, the combination of both of that to get the reranking module. Next, we'll see the results, how cross-attention improved the results for retrieval, what are the benefits of reranking, and some comparison with the state of the art in this particular domain. Finally, we'll be concluding the session with this.
Thank you for the introduction. Thank you for the outline. Let's go to the introduction. So the task here is basically do a language-based search of large-scale image and video dataset, which means that there is a text Y. Let's say there is a dog riding a bike. Then I have to respond with a set of images, a ranked set of images, like these are most relevant, this is least relevant to the user. So the approach which is generally taken in the community is to independently map this text and vision to a joint embedding space. So for instance, there is this X being the image, so we can map it to some embedding FX. Y being the text, we can map it to some GY. And then after mapping, we can find some similarity between them. And according to that similarity score, we can say that these are most relevant, these are least relevant. The 2 generic approaches, the first is dual encoders, which are fast and are easily scalable to very large number of images. And this is simply we can speak as dot product, which is fx transpose into gy. So this is very fast. The second is the cross-attention mechanism, which is slow, but the benefit is that it improves the retrieval accuracy. But since it is slow, hence it is inapplicable in practice due to these scaling problems, like computationally heavy, very slow, and hence if we start scaling it to large number of images, it will cause problem and the time taken will be very large. The contribution this paper makes is making these fast DE modules more accurate. How they're doing that? They're using a distillation objective. They're using a knowledge distillation to transfer the knowledge from the accurate and slow cross-attention models into this DE models. So this will ultimately result this fast DE models being more accurate. The second is that they're using both this slow and the fast models by combining them to re-rank the very few images that are being obtained from the fast model. So the approach can be very simply written as using this fast DE models. So from this point onwards, we will use fast for DE and slow for cross-attention models. So they're using the fast models for retrieving, let's say, some K images. K can be, let's say, 10, 50 or something like that. And out of these 10 or 50 images, they will use the combination of fast as well as the slow models to give a ranking of them. Like let's say the third image should be ranked first, the second image should be ranked second, 10th image should be ranked third, something like that. Out of this, let's say K equal to 10. So this is the output they want. Now, so you may ask that, okay, just by using the first model, we can get a ranking between them, but that may not be completely accurate. Hence, they're using the slow model to re-rank, like a combination of both of this. Another point is that why the slow model is applicable to this 10 images and we are not using it for the large number of images. That is mainly because since the number of images is very small, so this will not affect the inference time if we use the combination of slow and fast. Now they also provide, they also show that the inference speed increases while keeping the retrieval accuracy competitive to the state of the art on various dataset. So for the image domain, they test on Flickr 30K, and for video domain, they test on Vertex. So they train on MS Coco as well as another dataset called CC, conceptual captions. Now, first of all, we will see a very brief outline of dual and encoder and the cross-attention models. Then we will deep dive into how this knowledge distillation is happening, what are the captioning laws they're using, and everything else. So first of all, this dual encoder, as described earlier, they are very fast models. And this is because if the vision or if the visual part or the image is given, we can use a vision network to encode them. It can be, let's say, f of x. And if the text is given y into a text network, we can get g of y. Then the similarity can be computed simply by taking a dot product between them. So it extracts modality specific embeddings, and then the similarity can be found using the dot product. So this is a very fast mode. And in the cross-attention network, the approach is similar, like we are feeding x and y, but the final assumption is that this x comma y, which is basically similarity between the image x and text y, cannot be decomposed into simple dot products. Hence, it cannot be just fx transpose into gy. So they're using some complex convoluted mechanism here, which is simply cross-attention, and this allows rich interaction between the image and the text. Hence, increases the accuracy, but simultaneously decreases the inference time. So first of all, let us see what this cross-attention models are. So as we saw in the previous picture, they are going to give this value hxy for an image x and input text y. So this phi x can be any visual encoder such as CNN, and this y is the text part. So this A is the network which performs the cross-attention mechanism. Maybe A can be a transformer decoder, something like that. So it will take the input phi x, it will take the input y, and then it will give a final number hx comma y. Okay. Now the authors here propose two novel methods. One is so they address firstly one problem that in general approaches, this phi x or the output of the visual encoder is most of the time downsampled and not containing enough information to be used in the cross-attention mechanism. So they provide one novel technique there, which is being used. And the second thing is, while doing this training of the cross-attention mechanism or the cross-attention module, people use the contrastive loss. Rather, they have used the captioning loss to do this retrieval, and they show that how captioning loss is competitive and how it can be also related to the contrastive idea. First of all, let us see what the generic approach for doing the phi x, like encoding the vision part. We generally take the last convolutional layer of CNN. So if you consider a resonate 50 architecture and the input image is 224 by 224, the output will be a 7x7 feature map, which then can be flattened into 49 vector. And those are like 49 vectors, and there is the text part y. Then somehow we can use, let's say, a transformer decoder, which will do the cross-attention mechanism between these two and give the value hxy. So just to reiterate, the task of this cross-attention part is to give the final number, this hx comma y. Now, while the last feature map, it produces a high-level semantic information, but the problem is that sometimes this feature map is severely downsampled, and there might be loss of large amount of information, which should not be sufficient for grounding. So what can be the very first idea that comes to the top of the mind? An idea could be just increase the input image resolution. Let's say instead of 224, we can increase it to some 384 or something more than that. But the problem will be that it will increase the cost of running this entire backbone. So since there is an image being provided here, we can again go to the problem that we can face. The problem is that in this 7x7 plus 248, the information that is being obtained is severely downsampled. We want to use something which is containing more information before feeding it into the decoder. So this is the thing that we're going to feed it. And instead of feeding the output of the final layer of the CNN architecture, we want to feed something else which contains more information. So what they do is they do a gradual upsampling with a very lightweight architecture. And in each step of upsampling, they're using the information from the CNN backbone or the visual encoder backbone to do the upsampling. So that's the idea basically here. And ultimately, they're obtaining this phi x. Now with this phi x and this query y, they're going to find the similarity h of xy. Now the cross-attention thing is happening here using this transformer decoder, and we will see in the next slide how exactly that is happening. So yeah, they're using captioning model for retrieval. Okay, now what they're doing is in the cross-attention module A, it is a stack of transformer decoder, and it takes the feature map phi x as an encoding state. Like here, this is phi x is input to the transformer decoder, this arrow part. Then each layer of the decoder consists of a text self-attention layer. So inside this decoder, there will be self-attention layer between the text part. Then there is a cross-attention layer that enables the text to attend to visual feature. Like there will be a cross-attention, like that's the name of the entire mechanism, cross-attention. So there will be cross-attention between the input phi x and the query y. So for doing the cross-attention, we can consider this value as like in the previous slide we saw that if it is 7 by 7, then we can flatten it into 49 such vector. So here it can be 56 and 56. Let's say that number is n. So n such 512 dimensional vectors. Okay, so there'll be cross-attention between these vectors and the text query y and the final feed forward layer. The important point to note here is that the absence of the self-attention layer on the visual feature, like there will be no self-attention in this visual feature. Hence the profit or the gain is that we can increase this n to very large numbers, since there will be no problem since there is no self-attention in the visual part, this n can be taken into very large values. And in the results part, we will see that they're comparing by taking various different number of features. Okay. So that's what is written. Allow visual feature maps to scale to thousands of vectors. Now we will see how exactly this entire thing is going to be trained. So we require a loss and backpropagation. Okay. So first of all, the input text y is this, like the length of the input text is capital L, and it is represented like this. So this is the output of the CA model. That's what we have been talking all about. And they're decomposing into two parts. One is the forward and one is the backward, hence the name bidirectional captioning. So we will see how H forward is being defined and H backward will be similar to that. So H forward is simply the sum of log probability in the language modeling task. So for instance, in language, let's say the text is that has been generated till now is a dog, and that is this blank. So this YL will be what is the term, that is rights, and then this section will contain a and dog. This phi x is the input from the visual part, and theta forward is the parameters for the forward for doing the forward captioning. So it will be summation of all of those. Like first it will be generating log prob of a, then it will be log prob of dog, then rights, and so on. Like if we go back to the image again, we can see that we have to predict this. Let's say a and dog is already there, the exact example that I have told, and when we want to find the probability of rights, then it will take this phi x, this already generated input a and dog, and the theta forward parameters to find the h forward value, to find the L value, and then taking the sum of all of this, we can find the hxy. We will find the h forward xy. Sorry for slight notation abuse, but okay. So similarly, this is h forward, and we can find the h backward by doing exactly the same thing, but generating the text in the reverse direction. Now we want to have a loss so that we can train this visual backbone, the forward and backward transformer. So forward transformer is responsible for giving this h forward, backward for giving the h backward. And the loss we are using here is the doing the captioning loss, like summation of all this h for each xi comma yi pair, and that's it. Like we have a loss, we can backpropagate, we will train the visual backbone, forward and the backward transformer models. That's it. That's all about training the slow transformer based cross-attention model. Now for the comparison between captioning loss and the contrastive loss. So one thing if you observe here is, so we are trying to predict the probability of rights, and I want this rights to be high depending upon the input phi x. Okay, and so this in some sense also means that a dog, let's say, walks or runs or fetches, the probability of these kind of sentences given this phi x, which is responsible for this image, is going to be low. And that's in some way we are taking all the tokens, all the other token other than the token rights as negative. That's what they are mentioning here. Okay, now so we'll continue.
Yeah, like that was quite good. That we understood how the slow model basically works. Now let's see what they exactly do about the faster model and what exactly they proposed. So the author proposed a knowledge distillation for the slow cross-attention model. It is quite evident and intuitive that the cross-attention model would perform better on this retrieval task, but as it is a heavy computation-based approach, it is not advisable to use at the first step. So basically, they try to distill the knowledge from that model into the fast dual encoder model, which simply use the dot product as similarity score. Finally, during the re-ranking mechanism, they combine the fast dual encoder model along with the slow cross-attention model via a re-ranking mechanism. Okay, so let's see. Okay, the approach of calculating the similarity between the text and image lies with the calculation of dot product between the representations. Let's say we have an image X and we have a text Y. Then the semantic embeddings will simply be f of X and g of Y. Now, the task is that relevant image text pairs should have higher similarity. And this is a straightforward task that uses the contrastive loss. And it goes like, let's say we have the image embedding fx and text embedding gy. And if they're relevant, then this particular numerator in the contrastive loss has to be higher. This means that the similarity between those two image text pairs will be higher. And how do they like calculate the denominator or normalizing thing? Like they sample negative pairs, that is they get negative pairs, like for a particular image they find some different captions, and the similarity between those two representations should be different. And this is the basic motivation behind the noise contrastive loss.
Yeah, maybe you can try to get access to the pen. Like, can you try once again?
Yeah, let me try. Yeah.
Try to write something.
No, it's.
I still can't see it.
No, I also can't see. I think.
Just a moment. Oh, highlighted, yes. Okay, arrow options, it will be visible. I guess I have to continue then. Okay, then maybe we can do that also.
Yeah, let's do that.
Yeah.
You can.
Okay.
No, yeah. Okay, let's move on to the next slide. Okay, so the authors, like in this setting, the knowledge distillation basically works in the classification task, but here the authors extended the distillation approach, and for that reason they created or sampled a finite subset of image text pairs, which comprised of, like, let's say we have a image text pair, and keeping that particular text, the author sampled some random images, and that became the negative thing. Like xi yi is the relevant image text pair, and x comma yi is some random pair. Okay. Now the probability distribution measuring the likelihood of any pair of image and text that belong to this particular set, let's say bi. According to the slow teacher model hxy, is written by this expression. Okay, so what does this exactly mean? So we have the similarity from the slow teacher model as hxy. We find e to the power hxy divided by sum over all the samples present in the set B exponentiated. Also, you can see that there is a parameter tau, which is nothing but the temperature parameter that is used for smoothing the probability distribution over the random variables. Okay. Moving ahead, a similar notion is also used for the fast student model to calculate the probability distribution over the image text pairs. But instead of using hxy, we just replace it with the dual encoder similarity notion. That is simply the dot product between the image embedding fx and the text embedding gy. And rest all of the things remain same. So we get by this we get the distribution of the dual encoder model. And as the motivation lies for knowledge distillation, like the student model should have a distribution similar to the teacher model. So for that reason, the authors propose this distillation loss, which is nothing but the cross entropy between the probability distribution found by using the slow cross attention model, which is PBI, and the probability distribution found by using the fast dual encoder model. And our aim is that the distribution of dual encoder should be similar to the distribution of cross attention, which has already been trained by a slow mechanism that has already been discussed. Okay. So moving ahead, the final loss is the combination of standard contrastive loss with the distillation loss. So as we saw, like the contrastive loss tried to map the semantic embeddings of relevant text image pairs to a closer space, whereas irrelevant image text pairs are far apart, while the distillation loss tried to mimic the dual encoder model to the slow, robust cross-attention model. So basically, this serves the purpose of making the dual encoder model quite efficient and accurate as the cross-attention model, as well as it also tries to separate irrelevant image text pairs in the representation space. As you can see, there is a hyperparameter alpha greater than 0, which simply determines what is the contribution of the contrastive loss to the final loss. Okay, so once the distillation is done, like the dual encoder model is trained by using the combination of both the losses, next comes the re-ranking step. So the first step is to obtain a crude retrieval, that is by using the dual encoder model, which somewhat mimics the slow cross attention model. The authors tried to retrieve, let's say, top k images, let's say 10 or 50 or 100. And finally, using only the dual encoder, it is not as robust as the cross attention model. It cannot simply be used for re-ranking the images that are being retrieved. So for that reason, the authors use the combination of both cross attention model as well as the dual encoder model, which can be seen in this equation. That is, the hxy is the similarity that is being found by the cross attention model, whereas fx transpose gy is the notion of similarity used by the dual encoder model. And a linear combination of these two similarity scores basically gives the relevance or similarity score of an image text pair. So more is the similarity score, or more is this particular linear combination, the higher the relevant that particular image text pair is, and that will be ranked higher in the final ranking. Note that here another hyperparameter beta is being used, which basically weights the output scores of the two models, that is cross attention and dual encoder. So if beta is high, then we are giving more weightage to the scores of dual encoder, and if beta is low, then cross attention gets more weightage. Okay, so let's see some of the results. There are basically, the approach is quite clear, I guess. So The authors intuitively, it shows that the cross-attention model is being trained quite robustly, and it evidently also performed better than the dual encoders. As we can see, like the fast NC, BOW and NC BERT. BOW is nothing but simply it means bag of words model. So fast, these two models are dual encoder type, and the F R at 1 score and C R at 1 score, all correspondingly R at 5 and R at 5 for F and C. F is nothing, is simply the Flickr 30K dataset, and C is basically the MS Coco dataset. Okay, so the dual encoder model has comparatively less score than the cross attention model. This shows that the cross attention models are robust. Also, captioning models are surprisingly good for retrieval. So let's see the second set of rows in the table, that is comparing pixel BERT and vertex forward only. Vertex forward works on the contrastive loss stuff, but pixel BERT works on the contrastive stuff, but vertex forward only works on the captioning loss. And as you can see, evidently that the recall scores for vertex forward is better than the pixel BERT model. Okay. There is one thing to note, that the bag of words model has better recall score than BERT model. So, but this can intuitively say that the complexity of language model does not matter for the relevance of image text pairs. Rather, how are the scores combined using the cross attention? Like how is the visual output and text output combined for using cross attention? That is more relevant for the accuracy of this retrieval task. Now coming to the next table, this basically shows the benefits of upsampling architecture design. Let's consider vertex conv v5. The output is simply a 7x7 feature map, and that is, let's say, being upsampled to 96x96 feature map that is done by the slow cross attention model. As we can see, the recall score was around 38.1 in Flickr 30K, but it rose around 6% to when upsampled to 96x96. And similarly for MS Coco dataset also we can see the rise. So this indeed proves that the gradual upsampling also helped in better retrieval scores.
So in this table, we see the performance of combining both re-ranking and distillation, and see that it provides better performance than other approaches. So first of all, this K value is basically the number of images being retrieved by the crude retrieval step, or the first D step, first D model. So since we are using only slow model in the first row of both the parts, there is no value for K. K is not defined, and distillation is not being done since the distillation is from slow to first model. And these are the results, and the notation is exactly the same as mentioned in the previous slide. Now, if we closely look at these two and these two, we see that by adding the distillation step, like DE distilled with the slow model, like the slow CA model, we see that there is an increase in the results. So this provides support to the fact that this distillation helps the DE model to being fast and also improve their accuracy. Like it makes them fast and as well as accurate. So similar trend is also being seen here, like in case of when top K value is 50. Now the next thing is in this set of rows, like in this set of row or in this set of row, we see that the maximum performance is always in the last row, which is basically using the K value as 50 along with the distillation. So this is, so in this particular setting, we are doing the re-ranking with the fast and slow, and in the retrieval step, we're retrieving 50 images with the distilled dual encoder models, and we see that the results are the best. In this table, so this table will be the final table, but in the paper there are a couple of more tables as well as some more analysis. We direct you to read the paper. The paper is a fantastic paper as well as easy to understand. So yeah, we will request you to go read on that paper for more details. So this table basically shows the comparison with the state-of-the-art approaches. So in this two row, we see that compared to Wilbur, their approach with K value equal to 100, they see that the increase, the value is high, across all the recall, like recall 1, 5, and 10. And the dataset they're using is Flickr 30K. And they're training the models with on CC, which is conceptual captions. The next thing is in this set of rows, in these two rows, we see that using the pixel bud with Resonate 50 backbone and also using the fast and slow with the Resonate 50 backbone, they're observing improvements within the recall 1 and recall 5, but slight decrease in recall 10. However, the recall 1 and recall 5 is a difficult task. Like you have to find the correct image in the 1 and the 5. Like in the top recall, in the 5 images, you have to evaluate the recall value, but here in the 10 images. So that's why they're doing better compared to the state of the art, or we can say they are giving competitive results. And all the while they're maintaining the inference speed also. So that's good. And these are all various other results with different training data set. So VG is visual genome, and you can see all the other data set present in the paper. So yeah.
Okay, so let's conclude the session by just summarizing what the authors proposed. So the authors proposed a very accurate and slow text vision transformer based model that used the mechanism of cross attention between the visual feature maps and the text. Now using that visual like slow cross attention model, they distilled the knowledge to a fast dual encoder model, which was used for the crude retrieval as the first step that retrieved, let's say, some 50 to 100 images. Finally, to re-rank the retrieved images from the crude retrieval, they combined both the cross-attention model and the dual encoder model to get a linear combination of their similarity scores, and they finally re-ranked all the retrieved images to get the final ranking. This also showed that during inference, it gives faster result because the dual encoder model retrieves does the crude retrieval step quite fast. Thank you.